So we've got like one last math club this semester, by the way, on Friday. Matt McCauley has a business game, we get the ADM seminar math club. So it's about Catalan, so it might be kind of interesting for a lot of you. I'd encourage you to be there. There's also the math in on Friday, so put that on your radar. So I gave you some examples last time. Formal power series over a field. Z localized as non-zero prime P. These all have value from Z. By the way, on these, there's a way that you can use that valuation to actually make a metric. And I made the note last time, unfortunately, we don't have time now. If y'all wanted to talk about that next week during our final exam, sort of talk, and maybe talk about this, but on the integers, you have your ordinary absolute value, and if you complete those, then you're sitting in analysis, and you do get the real numbers. You can also use the metric induced by this valuation here. The adding. It's also a nice metric space too. In fact, in a certain sense, it's too nice. It's nice. The triangle inequality is so good there that, for example, any triangle in the space that you put there, any triangle is isosceles. And if you have any circle, any interior point is the center, which is kind of bizarre, right? But Z is sort of the easiest value group. One of the things I let you with last time is well, one thing that I could do to make this put some kind of ordering on this. I could declare two ordered pairs and C sum Z. This is less than or equal to this if the first coordinate is greater than or equal to the first coordinate here, second coordinate greater than or equal to the second coordinate here. Now, this is in fact partial ordering, right? Because it is AB is less than or equal to AB, right? It's transitive, it's clearly transitive, and it's anti-symmetric because if A is less than or AB is less than or equal to CD and CD is less than or equal to AB, then they have to be equal. Right? But this is not a total order. For example, 0, 1 and 1, 0 are not comparable. So you've got apples and oranges in your basket here, right? Anybody see a way to make Z sum Z a total ordering, so a variant, this so to speak? So what's that? So, and how do you mean that? Plus B, that's the right, but I have some doubts about whether that'll be transitive. Well, I guess it would be. So here, so let's go through it. So is this what you're proposing? Uh, Well, certainly, got that. We also need anti-symmetry. So that's pretty common. Which just means that A plus B. So for example, you have 2, 3, and 4, 1, but these are not equal. So noble effort there. How many of you have ever been to the library or one of these places? If you're going to look up a book in the library, in the card catalog, whatever, or if you're going to look up something in the index of a volume or whatever. So suppose you wanted to look up ideals in your algebra book, right? What's the first thing you do when you go to the index? If you're going to look up the word, well, so suppose you're in the encyclopedia and you want to know everything about Tyrannosaurus Rex, right? If you're looking in the encyclopedia for Tyrannosaurus Rex, what's the first thing you do? Find the T's, right? Well, there's quite a lot of T's in the encyclopedia, right? So what do you do next? Then you go to the Y, right? And then the R and so forth. This is the idea behind here. We're going to go to the library, just these few things. So here's what we're going to do. And I hope you see how you can extend this as well. We declare A is less than C, or A equals C and B is less than, which is exactly what you do when you look something up in a dictionary or an index. So if A and C are different, whoever has the smallest leading term is the smaller. If you have a tie, your second coordinate is the tiebreaker. So let's go through it. This is a checkamundo, right? Because we have a tie in the first coordinate, and then in the second coordinate, B is certainly less than. Right? 2. Suppose A, B is less than or equal to C, D, and C, D is less than or equal to A, B. Well, these two conditions right here, this means that A equals C at the beginning, or A equals C, right? Because if A was strictly less than C, then that can't happen. And if A is strictly greater than C, then this can't. Right? Then that one can, right? And since A and C are the same thing, this means that B is less than or equal to D, and D is less than or equal to D, so D and D is C. So we get anti-symmetry here. Everybody okay with that? And finally, 3. And, you know, you can get on your bulldozer and go through some cases, right? If A is strictly less than C and C is strictly less than E, then A is strictly less than E in these holes. And then go through the cases where you get some ties. But this will, is everybody okay with transitivity here? Okay. So that is how you take two copies of Z and turn them into a totally ordered theory, because it's clear, isn't it, now that everything can be compared. Any two A, B, and C, D can be compared because Z itself is totally ordered. You can replace the Z's by Q's, you can replace the Z's by R's, you can replace the Z's by any totally ordered Abelian group. And you can also expand this, right? You can have three copies of Z and just do the library thing again, right? Compare the first two, compare the second two. Now, I've given you a number of valuation domains where the value group is Z. Does anybody see how to build a valuation domain with this? I'm gonna build two more valuation domains. I'm gonna build a valuation domain with value group Z sums in and show you how to make it bigger. I'm gonna build a valuation domain of value group Q or R, something like this. Okay, so here's what I'm going to do. I'm going to start with the following instruction. And I'm going to look at this ring. This is a ring that contains a polynomial ring of two variables X and Y, but I've thrown in these other rational functions, right? I've also thrown Y over X, Y over X squared, Y over X cubed. Effectively, what that does is in this ring, X divides Y as many times as you want it to, right? Because X divides Y because X times this is equal to that. And X divides Y over X as well, because X times Y over X squared is Y over X. So like you can suck any power of X out of a Y over X. Now, what I'm going to do is I'm going to let M, I'm going to call this first ring R, and I'm going to let M be the maximal ideal generated by so just take this ideal, this is generated by these crazy rational functions, X, Y, Y, et cetera, et cetera. And notice that R mod M is field, right? I mean, basically R mod M is you turn this all these into zero and you get a field. So this is indeed a maximal ideal. Now I'm going to be a little fast and loose and intuitive with this. I'm not going to go through a formal proof, which is a little bit grungy. But now let's let B be R localized to M. So that is what I've done in R is when I localize it in, I take everything that's outside of this maximal ideal. That is everything everything in here can be made sort of this polynomials and all these kind of random rational functions, right? It's sums and products and powers of these things, plus constants from the field, right? Anything with a non-zero constant that is something outside of the maximal ideal is now turned into a unit, right? So in this ring, you have 1 over X, you have 1 over Y squared plus Y over X squared plus Y to the 7th over X to the 24th. All these things are units, right? And in fact, the maximal ideal here is is MRM. Now, let me kind of show you something interesting that goes on here. You know what that element is? Looks like a mess, doesn't it? I think that's good. So that element is X. Doesn't appear to be, does it? But let me show you what happens here. I can pull an X out of everything in here, right? Because remember, I can pull any number of X's out of powers of Y that I want. And notice this is a unit indeed. So this is X times U. So it's essentially X. It's just an associate of X. It's X times U, right? Let's see my original. Give me any element of maximizability one. Try them. My claim is this is a monomial times U. Anybody see what it is? Let's see, this can be down to Y. Executing from plus Y X8 plus Y5 X24. That looks right to y'all. And this is the unit. So this is Y squared of X4 times U. So this is just essentially the monomial quantity of X4. Let's look at these monomials, shall we? Suppose I have in this ring, can you tell me what the restrictions on K and M are? Well, not necessarily, because so if n is 0, then k is greater than or equal to 0. Right? Because if n is 0, I can't have negative powers of k. Right? But if m is greater than or equal to 1, then k, there's no restriction. N is 1. Now notice, how do we compare these? So suppose I have x k1, y m1, and x k2, y m2. I claim that I can compare any two, that one of those two monomials must divide the other. Right. Can you tell me how to tell? How do I compare these? Which one divides the other one? How do I tell? Oh. If M1 is less than M2, then this quotient will be and another restriction I failed to put down here is M is greater than or equal to 0 in its range. If M1 is less than, strictly less than M2, then the quotient is y to the M2 minus M1, x to the K2 minus K1. In this case, this is positive. And so the power of x can be willy-nilly positive or negative. Right? It doesn't matter. If M1 is less than M2, then this divides this. Or if M1 equals M2, if the powers on the line are the same, what do you need? So now if you're dividing these are going to cancel. Now you're going to need K1 is less than or equal to K2. And the quotient here is x to the K2 minus K1. And this is greater than or equal to 0. This looks familiar, doesn't it? Isn't this the library order thing? We compare the exponents of y first. If one of them is smaller than the other, it's the divisor. If it's a tie, then whichever name compare the powers of x, right? This shows all monomials are comparable. Which is why my two examples work, right? If I wrote down a string of monomials, you think, oh my goodness, this is always a polynomial. One of these monomials is the smallest, correct? In this case, it turned out to be whichever one is the smallest, I can pull it completely out, leaving a 1 plus some other garbage, which is a unit, right? So in particular, evaluation. B is valuation domain because any two elements elements. B, well, we'll say non-zero. Are of form x to the k y to m u, where m is greater than 0. If m is bigger than 0, k is anything z, and if m equals 0, then k is in fact u. And any two such elements can be compared. So this is evaluation. And here's something interesting. It might be a little bit, yes.
So this reliable is breaking down, breaking down the unit. What would that look like for y over x plus y over x squared?
What's that now?
Y over x plus y over x squared. Because it seems like that will give you 1 plus 1 over x. Or probably supposed to be a unit. So how do you decide which one you're going to use? Because
The small one with regard to valuation, right? So these two are a tie. So this is y x. You compare the y's first, you get a tie. And now you compare the x's. This one's smaller. So that's what we'll pull out. Did I answer your question?
I guess I'm a little bit confused, but I thought we were first pulling up units and then comparing, and then using the valuation to compare the two. Like,
No, what I said at first is any pair of monomials is comparable. Right? So so when you write a sum like this one right here, that means you can pull this thing out. You can pull out the smaller one, and now you have the smaller one times a unit. Well, now in general, this is what a typical element looks like. It's a monomial times a unit. And that makes it easier to see that they can be compared. Just if you have xk1 ym1 u1 and xk2 ym2 u2. So I've taken these things and already gone through the pull out process.
So we kind of are using the valuation twice. The first time we'll find out which coefficient to pull out, and the second time actually compare the two coefficients.
Right, compare the total element. Right, that's right. By the way, it's interesting to note that for this valuation thing, for B, this is actually, so let me write the zero ideal. So there's that one. Does anybody know what the maximal ideal looks like? Well, the maximal ideal, remember how I said the maximal ideal in R localized N is X. So the maximal ideal should look like this. It should correspond to the maximal ideal here. But this ideal is actually principal. Right, because X divides every one of the generators. Right? And there's another problem. This one is not finitely generated. Which is weird, isn't it? Right? Because you have the zero ideal, you have a principal maximal ideal that's generated by a single element. But then when you strip that X out of there, then you have this prime ideal here. That's in between here. And by the way, these are the only prime ideals. And evaluation domain, all the ideals, including all the prime ideals, there's only three prime ideals. Maximal ideal, which is principal, the zero ideal, and this ideal in between that is not finitely generated. Any questions on that? By the way, you can do the same thing for three variables. If you want three copies of C, do an analog of this, 4 or 5. You can make these things very, very big. And even though valuation domains, well, we can do one example. Here I'm going to start off with a different. I'm going to start off with the following group ring. I'm going to write a notation for this that I hope is convenient. This is the set of polynomials alpha 0 is alpha 1 x q1 alpha n x qn, where where alpha I is in F and QI is in so this is just like polynomial rings over a field, except I'm giving you a little bit more freedom. I'm allowing you to let the exponents, instead of just being positive integers, I'm allowing you to let the exponents be positive rational numbers. Right. Once again, I'm going to look at the maximal ideal generated by x to the alpha power, or alpha and q, alpha bigger than c. So I'm going to look at the maximal ideal, this polynomial ring generated by all powers of x, rational powers of x that are strictly positive. And again, R mod m is isomorphic to these fields. This is maximal ideal. And I'm going to make a valuation domain this time, the R localized in, just as I did before. So anything that starts with a non-zero coefficient as before is a unit. Anything whose first coefficient is 0 is in the maximal ideal. And notice that we have the same thing going on. Let me just make up some stuff. Notice that Q is a totally word revealing group, right? Now, all I got to do is look at this sort of polynomial, if you will, and ask myself itself, what is the smallest exponent that I see size-wise? Looks like it's 1. So I can pull this out. 1 plus 2. You have this. That's how many 12s. 8 minus 8 is 5 12s. X to the 7 4s plus x 15 4s minus 7x to 9 4s. And notice this is a unit. So just like before, I can pull out the smallest exponent that I see. And in general, every non-zero element is a form x to the alpha of unit, where alpha is greater than zero. And fourth right. That means we can again compare any two non-zero elements. Take x to the alpha u1, x to the beta u2, whichever one has the smallest positive rational exponent divides the other. Okay. This is a valuation domain value for q. As 0 and m, v has its prime ideas. But here MV is not principal. Because actually remember, this is valuation domain. So every ideal that is finitely generated is principal, right? So if the maximal ideal here was finitely generated, it would have to be generated by a single element. And that element would have to be in the form x alpha. But x to the alpha can't generate that, because how are you going to get x to the alpha over 2? Right? Because multiply x to the alpha times something to get x to the alpha over 2, you effectively need x with a negative exponent, which can't happen. So this is an example of a one-dimensional valuation domain that is all non-zero prime ideals are maximal, but it's not in theory. These things can be built all kinds of crazy ways. I can build valuation domains where, yes.
So you have that one list of units. Well, I'm going to 1 plus 2.
Right.
So before we were saying stuff in a full power series is a unit. If it like it has a coefficient, or sorry, if it has a constant term, it's not 0. But when you wrote up, I'm sorry, I should have said maybe erased it. When you brought up there, you had finite, it looked like you had R being all these finite in many terms.
Mhm.
So how do we know that this is a unit in this case?
Because I localize it. This thing, this piece is in the maximal ideal. Did I localize that? This piece is not in the maximal ideal because I added 1 to it. And so since it's not the maximal ideal in the localization in terms of, so it's not the same as the power series already has that there. But when I pass, so the original R. So these are polynomials that look like. Right. Now we have this maximal ideal that's generated by x to the alpha power. Right. And this piece right here is in that maximal ideal. So 1 plus this piece cannot possibly be in that maximal ideal. Because if this whole thing were in the maximal ideal, this piece is already in the maximal ideal. This minus this gives you 1 in the maximal ideal, which is possible. And when you localize, this is the set of R over S, where R is an R, and S is not in the maximal ideal. So in particular, this thing not being in the maximal ideal is now a unit. Any other questions? And even though valuation domains have always seemed to me to be pretty hyper specialized, right? It's like giving you a pair of elements, one of divides the other. You can make these things all kinds of crazy, right? I've given you a couple of Noetherian examples. I've given you a couple of non-Noetherian examples, including one that has a chain of 3 prime ideals. I can make that chain infinitely long. I can make it as long as I want finite. I can make it infinitely long. I can make it where the maximum ideal is principal. I can make it where the maximum ideal is not finite generated. I can make it where it has no height 1 prime ideal. And what I mean by that is you've got the 0 ideal. If I walk up to you on the street and give you any prime ideal in that valuation domain, there'll be another one in between. Right, so there's these things are crazy, and hopefully we're going to see the importance of this pretty soon. But let me give you valuation domains have a number of nice properties. And this valuation also gives them the property that any 2 elements are comparable. This means that any finitely generated ideal has to be principal. Here's what else it means. All the elements are linearly ordered. That, and what I mean by that is giving you 2 elements, you can compare one of them by the other. This means also that all the ideals are linearly ordered. So the tree of ideals in this thing is just straight. There's no branches. All right. Here are some other nice properties. Proposition. Any valuation. It's completely closed. I don't know why, but I was thinking. Actually, completely integral close is almost never true. It's an integral close. Okay. Let me give you a proof of this and then a word of caution. Yeah, valuation domains are, in a certain sense, almost never completely integral close. So let V be a valuation domain. And alpha in K, an element that is integral. And we'll say not 0. I mean, clearly, if alpha is 0, it's already in the valuation domain, sure. If alpha is in B, then done. Because that's what we want to show. So we will assume that alpha is not in B. By the way, if alpha is not in B, what does that say? Because this is a valuation domain. Right? Remember, one of the equivalent characterizations of valuation domains is for anything in the quotient field, which alpha is, either alpha itself or its inverse has to be in B. So if alpha is not in B, alpha inverse must be in B. That's the little linchpin there. Since alpha is integral, and this is one of the things Grant went over with you when I was at calculus challenge. Since alpha is integral, alpha must be alpha inverse. This is one of our characterizations when elements be integral. But if alpha inverse is in B, then we're done. So alpha must be in B alpha inverse, but since alpha inverse is in B, then that's statement means that alpha is in D. And there you go. Let me point out that, as I said before, so from this example that we did just a bit ago, notice that 1 over x is not in. Because in fact, x is in the maximal ideal here, so certainly it's not in, if 1 over x is not big. But y times 1 over x to the n, which is y over x to the n, is in B. For all n natural numbers. So B is not looking close. And in fact, in valuation domains, the primes are stacked, just like the ideals, primes are stacked vertically. If you have 3 or more prime ideals, that is, if the dimensions 2 or higher in valuation domain, it's never completely closed. Any questions? Here is another theorem here. 924. These are some things that I kind of bring up here. Maybe I can sketch this really quick. Theorem 924. Let V be a valuation domain, then V has the following properties. Any valuation domain V enjoys following properties. Number 1, the ideals of V are limited order. I'm mixing 4. That is, if you pick out any 2 ideals at random and V, one of them contains the other one. V is quasi-local. So so there's one and only one maximal ideal. Any radical ideal of V is prime. Maybe one of the things that Matt did in the first semester is any radical ideal is an intersection of primes. Well, primes here are linearly ordered. So in a valuation domain, any radical ideal is prime. And 4, any finitely generated I and B. Okay. I am going to give you a final definition here. This does appear on your next homework. See if you can prove those properties. None of the proofs of these are very difficult at all. And I think that working on that might give you kind of a better feel for this definition. 925. We say R is a Bezout domain And there's lots of French accents on this that I never can get or never can remember. We say R is Bayesian domain if every finite generated ideal of all things is principal. So if you believe the previous theorem, any valuation domain is quasi-local and Bayesian. So a Bayesian domain is where any finite generated idea is principal. You already know a nice large class of these principal ideal domains are Bayesian domains. Bayesian domains are just a little bit more liberal in following sense. Bayesian domains allow ideals that are not finitely generated. It's just all the ones that are finitely generated are principal. Every valuation domain that I showed you today has to be Bayesian, if you believe this. And there are other ones too, like the ring of entire functions on the complex plane is Bayesian domain. Okay, any questions? The ring of all algebraic interests. Well, any questions on that? All right, well, you all persevere and we will see you on Friday.